Hello there, welcome to my class. Today we'll talk about...
Let's try now to solve one problem for the DC analysis of our field effect transistor. Please try to consider these two methods when we analyze field effect transistor biasing. One is graphical analysis and the other one is mathematical analysis. In graphical analysis, first thing that we have to do is to draw the characteristic curve of the transistor. Then let's try to draw the load line and determine the Q point. So let's try to consider this problem. So this is a self-bias configuration. So given a self-bias configuration, let's try to find VGS, ID, VDS, VS, VGN, VD. Let's deal first with graphical analysis. So the first that we have to do is to draw the characteristic curve. How are we going to draw the characteristic curve? We have to use the Shockley equation ID is equal to IDSS 1 minus VGS over BP quantity squared. So from our problem, IDSS and VP are given. Why? Because they are part of the characteristic of our junction field effect transistor. Let's say that VGS is equal to 0. If VGS is equal to 0, then what would happen? 1 minus 0 squared will be equal to 1. Therefore, ID will be equal to IDSS. So therefore, when VGS is equal to 0, then ID will be equal to IDSS. So that gives us this point. ID is equal to IDSS. How about if VGS is equal to VP? Then VP over BP will be equal to 1. 1 minus 1 will be equal to 0. Then ID therefore will be equal to 0. So when VGS is equal to VP, this one is equal to negative 6. Then our ID, this one, is equal to 0. That's why we have this point. We have 2 points now. That is when ID is equal to IDSS and when VP is equal to VGS is equal to VP, which resulted to ID that is equal to 0. However, we cannot use that to draw a curve. So we need at least 3 points to have a curve. So let's say that VGS is 1 half of VP. So we have here VP over 2. If we substitute this value of VGS here, which is VP over 2, then VP over 2 over VP will be equal to 1 half. 1 minus 1 half will be equal to 1 half. 1 half squared will be equal to 1/4. Therefore, ID will be equal to IDSS over 4. So at VP is equal to 2, with VP equal to 6, that is equal to negative 3, ID will be equal to IDSS over 4. As we can see here, IDSS is equal to 8 over 4 is equal to 2. So we have this point. With that, we can now draw a line connecting these 3 points, and that becomes a curve. If you want, you can have other points. For example, let's say that VGS is equal to negative 1. What will be the resulting ID for that point? Next is we have to draw the load line. To draw our load line, what we need is the parameter or the equation VGS is equal to negative ID RS, which is our input loop equation. So again, we repeat this one, which is a graph that illustrates the relationship of ID and VGS. Since what is given to us is in IDSS up to 8 milliampere, so up to 8 milliampere, and we have here VP up to negative 6, so we can extend it, for example. So since what we are drawing is only a line, this time a line, what we need is only 2 points. Say, for example, that ID is equal to 0. So if ID is equal to 0, what will be VGS? That is also equal to 0. So we have this point. When VGS is equal to 0, then ID is also equal to 0. ID be equivalent to 4 milliampere. So substituting it here, 4 milliampere multiplied by RS, which is 1 kilo ohm, will result to VGS is equal to negative 4 volts. So with ID equal to 4 milliampere, what we were able to solve is a VGS that is equal to negative 4 volts. So connecting these 2 points and projecting it will result into what we call our load line. We can have also this point by substituting ID is equal to 8 milliampere, and that will result to a VGS that is equal to negative 8 milliampere. For the third thing that we have to do, let's determine the Q point. How are we going to determine the Q point? Let's combine these two figures together, that is our curve, characteristic curve, and our load line. So this results to this. We have now our characteristic curve and our load line. Take note of the intersection of the characteristic curve and the load line that will define what we call the operating point or Q point or quiescent point. Projecting that quiescent point to the right will give us the value for IDQ, and projecting it downward, that will give us VGSQ. Looking into the figure, we can see that IDQ will be approximately equal to 2.6 milliampere, resulting into a VGSQ also of negative 2.6 volts. We can already solve the value for VDS using the equation for the output loop, which is equal to VDD minus IDRS plus RD. DD is given to be 20 volts minus the IDQ that we were able to get using our graphical analysis equivalent to 2.6 milliampere multiplied by the total of RS and RD, and that will give us a value of 8.82 volts. How about VS? VS, as we know, is equal to the voltage at the source is equal to IDRS. That will give us also 2.6 volts. Using double subscript equation, that is VGS is equal to VG minus VS, as we have solved a while ago. Since VG is equal to 0, then VS will be equal to negative VGSQ. Therefore, VS is equal to 2.6 volts. So how about VD? VD is the voltage at the drain. Considering this loop only up to drain, then that will be equal to VD will be equal to VDD minus ID RD. VDD minus ID RD. And therefore, that will be equal to 20 minus 2.6 times 3.3 kilo ohms. That will give us 11.42 volts. Or, we can also use double subscript. VDS is equal to VD minus VS, resulting into the equation VD is equal to VDS plus VS. VDS is, we were able to solve it a while ago, 80.82, plus VS, which is 2.6. That will also give us the same value, 11.42 volts. So that's how powerful our double subscript equation is.